Greetings, viewer. Don't forget to visit my website for links to support the production of these works if you value what I'm doing. I appreciate any help you can offer. Thank you for having a look and a listen. Yours, JohnLothe. Understanding Physics, 3 volumes in 1, by Isaac Asimov. Read by JohnLothe. Chapter 5. Weight. The shape of the Earth. By determining the value of g, Cavendish had, in effect, determined the mass of the Earth. For this reason, Cavendish is often said to have weighed the Earth. But this is not what he had done. In common language, weight and mass are often spoken of as though they were the same things, and a body may be spoken of as heavy or massive interchangeably. Even physicists sometimes fall into the trap. However, consider what weight is. The weight of a body is the force with which it is attracted to the Earth. To repeat, weight is a force and has the units of a force. A simple way of measuring the weight of an object is to suspend it from a coiled spring. In accordance with Hooke's law, the force by which the body is attracted to the Earth will extend the spring, the amount of extension or strain being proportional to the force or stress. A weight measuring device of this sort is a spring balance. The mass of a body, on the other hand, is the quantity of inertia it possesses. By Newton's second law, mass equals force divided by acceleration. It is a force divided by an acceleration. By Newton's second law, m equals F divided by a. It is a force divided by an acceleration. Weight, which is a force, must, by the same law, be a mass multiplied by an acceleration. In the case of weight, which is the force of Earth's gravitational field upon a body, the particular acceleration involved is, naturally, that produced by the Earth's gravitational field. The weight, W, of a body, in other words, is equal to the mass, m, of that body times the acceleration, g, due to the pull of Earth's gravity. W equals mass times gravity. Equation 5-1. Since the value of g is, under ordinary circumstances, just about constant, weight may be said to be directly proportional to mass. To say that A is 3.65 times as massive as B is equivalent to saying that under ordinary circumstances, A is 3.65 times as heavy or as weighty as B. Since the two statements are usually equivalent, there is a strong temptation to consider them synonymous, and there lies the source of confusion between mass and weight. The confusion is made worse because of the common units used for weight. A body with a mass of 1 kilogram is commonly said to have a weight of 1 kilogram too. Footnote. The units of weight, pound, ounce, etc., were in use long before Newton established the concept of mass. The units of weight were borrowed and applied to mass, which was a mistake, but one which is now beyond retrieval. In the MKS system, however, the units of m are kilograms, kg, and the units of g are meters per second squared. Since weight is equal to mass times gravitational acceleration, mg, the units of weight are kilogram meters per second squared, or newtons. A kilogram of mass therefore exerts, under ordinary circumstances, 9.8 newtons of force. A kilogram of weight, which may be abbreviated as kg, Wt, to distinguish it from a kilogram of mass, is therefore not equal to 1 kilogram, but to 9.8 newtons. In the CGS system, g is equal to 980 centimeters per second squared. The weight of a body with a mass of 1 gram is therefore 1 gram multiplied by 980 centimeters per second squared, or 980 gram centimeters per second squared. Consequently, 1 gram weight equals 980 dynes. All this may strike you as unnecessarily puristic and refined, as making a great deal out of a distinction without a difference. After all, if weight and mass always vary in the same way, why bother so much about which is which? The point is that mass and weight do not always vary in the same way. They are related by g, and the value of g is not a constant under all conditions. The gravitational force, F, exerted by the Earth upon a particular body is equal to mass times gravity, mg, as indicated by equation 5-1. It is also equal to uppercase G times m apostrophe divided by d squared, or the gravitational constant times mass times the mass of Earth divided by distance squared, as shown in equation 4-1. Therefore, m times g equals uppercase G times m apostrophe divided by distance squared, or mass times gravity equals the gravitational constant times mass times the mass of the Earth divided by distance squared, or dividing through by m, g equals uppercase G, m apostrophe divided by d squared. Equation 5-2. Of the quantities upon which the value of g depends in equation 5-2, the gravitational constant, uppercase G, and the mass of the Earth, m-, may be considered as constant. The value of d, however, which is the distance of the body from the center of the Earth, is certainly not constant, and g varies inversely as the square of that distance. An object at sea level, for instance, may be 6,370 kilometers from the center of the Earth, but at the top of a nearby mountain it may be 6,373 kilometers from the center, and a stratoliner may take it to a height of 6,385 kilometers from the center. Even if we confine ourselves to sea level, the distance to the center of the Earth is not always the same. Under the action of gravity alone, the Earth would be a perfect sphere, barring minor surface irregularities, a fact pointed out by Aristotle. And then the distance from sea level to the Earth's center would be the same everywhere. A second factor is introduced, however, by the fact that the Earth rotates around its axis. This rotation means, as Newton was the first to recognize, that the Earth cannot be a perfect sphere. As the Earth rotates about its axis, the surface of the Earth is continually undergoing an acceleration inward toward the center of the Earth, just as the Moon does in revolving around the Earth. If this is so, then Newton's third law, see page 34, comes into play. The Earth's center exerts a constant force on the Earth's outer layers to maintain that constant inward acceleration as the planet rotates. The outer layers must therefore, by action and reaction, exert a force outward on the Earth's center. The force directed inward is usually called centripetal force, and the one directed outward is called centrifugal force, the words coming from Latin phrases meaning move toward the center and flee from the center, respectively. The two forces are oppositely directed, and the result is a stretching of the Earth's substance. If you were to imagine a rope stretching from the Earth's surface to the Earth's center, with the Earth's surface pulling outward at one end of the rope and the Earth's center pulling inward at the other end, you would expect the rope to stretch by a certain amount. The Earth's substance does exactly that. If every point on the Earth's surface were rotating at the same speed, the stretch would be the same everywhere, and the Earth would be perfectly spherical still. However, the Earth rotates about an axis, and the nearer a particular portion of the Earth's surface is to the axis, the more slowly it rotates. At the poles, the Earth's surface touches the axis, and the speed of rotation is 0. At the equator, the Earth's surface is at a maximum distance from the axis, and the speed of rotation is highest, just over 1,600 kilometers an hour. The interacting forces are 0 at the poles, therefore, and increase smoothly as the equator is approached. The stretch increases too, and a bulge appears in the Earth, which reaches maximum size at the equator. Because of this equatorial bulge, the distance from the center of the Earth to sea level at the equator is 21 kilometers, 13 miles, greater than the distance from the center of the Earth to sea level at either pole. The Earth, therefore, is not a sphere, but an oblate spheroid. To be sure, 21 kilometers, in a total distance of 6,370 kilometers, is not much, but it is still enough to introduce measurable differences in the value of g. What with an equatorial bulge and local differences in altitude, there are points in Alaska where the value of g is over 9.82 meters per second squared, whereas at the equator it is barely higher than 9.78 meters per second squared. That represents a difference of nearly 1/2 of 1% and is reflected in weight. In other words, the weight of an object changes measurably from place to place on the Earth's surface, as a spring balance would show. A man who weighs 200 pounds at the poles would weigh 199 pounds at the equator. To a chemist or physicist interested in the mass of an object, many properties depend on the mass. The measurement of weight as a substitute for mass would introduce serious inaccuracies. What the scientist usually does when he weighs an object is to make use of a balance consisting of 2 pans suspended from opposite ends of a beam that is pivoted at the center. Objects of known weight are placed on one pan. The object to be weighed is placed in the other. The known weights are adjusted to the point of balance. The force of gravity is then the same on both pans. If it were greater on one of them, the pan would sink downward, while the other would rise upward. If the weights are the same on both sides, then m times g is the same on both sides. However much g might vary from point to point on the Earth's surface, it is the same for 2 neighboring balance pans at one particular point on the Earth's surface. Therefore, the mass, m, is the same for the objects in both pans. The mass of the unknown object is therefore equal to the mass of the weights which is known. Footnote: mass is not completely constant, by the way. However, the variation in mass becomes important only at extreme velocities, not likely to be met with in ordinary life. Beyond the Earth. Naturally, the small changes in the value of g become larger ones if we alter greatly the distance of the body from the Earth's center. A further complication is introduced if in removing the body to a great distance from the Earth we bring it close to some other sizable conglomeration of mass. This situation is most likely to become important in connection with the Moon, for man-made objects have already landed there, and living men may be standing on the surface of the Moon before many years have passed. An object on the Moon's surface is still within the Earth's gravitational field, which extends not only to the Moon, but, in principle, through all the universe. However, the Moon also has a gravitational field. That field is much smaller than the Earth's, for the Moon is much the less massive of the two. Nevertheless, an object on the Moon's surface is much closer to the Moon's center than to the Earth's center. The Moon's gravitational attraction would therefore be greater than that of the distant Earth, and a man standing on the surface of the Moon would be conscious of the Moon's pull only. But the Moon's pull on an object on its surface is not the same as the Earth's pull on an object on its surface. To see how the two forces compare, let us refer back to equation 4-1, which states that capital F equals capital G times M apostrophe divided by D squared, or force equals gravity times the mass of the Earth divided by distance squared. This F refers to the intensity of the Earth's pull upon an object upon its surface. The Moon's pull upon an object upon its surface we can call capital F tiny m. Now, an object that has the same mass, whether it is on the surface of the Earth or the surface of the Moon, so m remains unchanged. Now, an object has the same mass, whether it is on the surface of the Earth or the surface of the Moon, so m remains unchanged. The value of g is also unchanged, for it is constant throughout the universe. The mass of the Moon, however, is known to be 1/81th the mass, m apostrophe, of the Earth. The mass of the Moon, consequently, is m apostrophe /81. The distance from the surface of the Moon to its center is 1,737 kilometers, or just about 3/11ths that of the 6,370 kilometers distance, d, from the surface of the Earth to the center. Consequently, we can set the distance of the Moon's surface to its center as 3 times d/11. We can now modify equation 4-1 using the mass and radius of the Moon to get an expression of the gravitational force of the Moon for an object on its surface. This is capital F tiny m equals capital G times m apostrophe /81 divided by 3 times d/11 squared. Or, the force of the Moon equals gravity times the mass of Earth /81 divided by 3 times 6,370 kilometers /11 squared. Equation 5-3. If we now divide equation 5-3 by equation 4-1, we find that capital F tiny m divided by capital F, the ratio of the Moon's gravitational force to that of the Earth's, is equal to 1/81 divided by 3/11 squared, or almost exactly 1/6. Thus, the gravitational force we would experience on the Moon's surface would be 1/6 that to which we are accustomed on the surface of the Earth. A 180-pound man who weighed himself on a spring balance would find he weighed 30 pounds. But though the weight was decreased so drastically, the mass of an object would remain unchanged. This means that the force required to accelerate a particular object at a given rate would be the same on the Moon as on the Earth. We could lift a 180-pound friend without much trouble, for the sensation of the effort involved in the lift would be like that of lifting 30 pounds on Earth. We could not, however, lift the man any more rapidly on the Moon than on the Earth. Now, we could manipulate something that felt 30 pounds with a certain amount of ease on the Earth. On the Moon, something that felt 30 pounds would have 6 times the normal quantity of mass, and it could only be moved slowly. For this reason, maneuvering objects on the Moon would give one the feel of slow motion, or of pushing through molasses. Again, if we jump on the Moon, the force of our muscles will be countered by only 1/6 the gravitational force to which we are accustomed on the Earth. The center of our body will therefore rise to 6 times the height it would on the Earth. Having reached this unusual height, we would then fall toward the surface, but at 1/6 the usual acceleration, 1.63 meters per second squared. This means we would seem to fall downward slowly, like a feather. By the time we reach the surface again, however, having dropped at 1/6 the usual acceleration for 6 times the distance, we would be landing at just the same velocity that we would be landing at from a similar jump, equal exertion, but reaching a much lower height on the Earth. To bring ourselves to a halt from that velocity would require as much force on the moon as it would on the earth. For it is mass that counts in this respect, not weight, and the mass remains unchanged on the earth. If we are seduced by our slow-paced fall into thinking we are indeed a feather and try to land gracefully on one big toe, we are likely to break that toe. The situation can be made even more radically unusual without having to go to the moon. The subjective sensation we call weight arises from the fact that we are physically prevented from responding to the force of gravitation with an acceleration. Standing on the surface of the earth, we are prevented by the substance of the earth itself from an accelerated fall toward Earth's center. It is the force exerted upon us against the stubborn opposition of the ground we stand on that we interpret as weight. If we were falling at precisely the acceleration imposed upon us by the gravitational acceleration, free fall, we would feel no weight. If we were in an elevator that had broken loose and was dropping without restraint, or if we were in an airplane that was in an unpowered fall, our sensation of weight would be gone. We could not press against the floor of the elevator or the airplane, since that floor would be falling as rapidly as we were. If we were in mid-air within the elevator, we could not drop to its floor, for the floor would be moving as fast as we were. We would therefore seem to remain floating in mid-air and to be weightless. Such examples of free fall are imperfect. Neither an elevator nor an airplane could fall for long without coming to disaster and ruining the equipment. Furthermore, the falling elevator or airplane would be slowed somewhat by the resistance of the air it was rushing through, and slowed to a greater extent than the man within the elevator or airplane would be slowed by the quiet air about him. There would therefore be the sensation of some slight weight. For the true feeling of free fall, we would need to be beyond the major portion of the atmosphere, say at a height of 160 kilometers or more above the surface of the earth. To keep at that height, it would be best if there were also a sideways motion that would keep one in orbit about the earth, in the same way that a combination of inward and sideways forces keep the moon in orbit about the earth. See page 42. This is exactly the situation in a manned orbiting satellite. Such a satellite is in free fall and can continue in free fall for long periods. The astronaut within has no sensation of weight. That is, not because he is beyond the pull of Earth's gravity, as some news announcers maintain. It is only because he is in free fall, so the satellite and everything in it are falling at precisely the same acceleration. The Earth itself is in free fall in an orbit that takes it around the Sun. Although its mass is huge, see page 52, its weight is zero. Cavendish, therefore, did not weigh the Earth, for he did not need to. Its weight was understood to be zero from Newton's time. What Cavendish did was to determine the Earth's mass. Even in free fall, where weight is zero, the mass of a particular body remains unchanged. Astronauts building a space station will be moving huge girders that will have no weight. They will be able to balance such girders on one finger, if girder and finger are motionless with respect to each other. If a girder must be set in motion, however, if it is already moving and must either be stopped or have its direction of motion altered, the effort will be precisely as great as it would be on the Earth. A man trapped between two girders moving toward each other may well be crushed to death by two weightless but not massless objects. The distinction between mass and weight, which seems so trivial on the surface of the Earth, is therefore anything but trivial in space, and can easily become a matter of life and death. Escape velocity. As an object is dropped from a greater and greater height above the ground, it takes longer and longer to fall and strikes the ground with a higher and higher velocity. If we use equation 2-1 and 2-2, see page 17 through 18, letting the symbol A in those equations be set equal to 9.8 meters per second squared, the acceleration in freefall, we can make some easy calculations. A body dropped from a height of 4.9 meters will strike the ground in 1 second and be moving at the moment of impact at 9.8 meters per second squared. If it were dropped from a height of 19.6 meters, it would strike after 2 seconds, moving then at 19.6 meters per second. If it were dropped from 44.1 meters, it would strike after 3 seconds, moving then at 29.4 meters per second. It would seem that if you could only drop an object from a great enough height, you could make the velocity of impact as high as you pleased. Certainly, this would seem so if the value of g were the same for all heights. But the value of g is not constant. It decreases with height. The value of g varies inversely as the square of the distance from the Earth's center. A point 6,370 kilometers above the Earth's surface would be 12,740 kilometers from the Earth's center, twice as far from the center as a point on the surface would be. The value of g at that height would therefore be just 1/4 what it is at the surface. An object falling from an initial state of rest 6,370 kilometers above the Earth's surface would in the first second attain a velocity of only 2.45 meters per second, instead of the 9.8 meters per second it would attain after a 1-second drop in the immediate vicinity of the Earth's surface. As the body continued to drop and approach the Earth, the value of g would, of course, increase steadily and approach 9.8 meters per second squared at the end. However, the falling body would not strike the Earth's surface with as high a velocity of impact as it would have done if the value of g had been 9.8 meters per second squared all the way down. Imagine a body dropped first from a height of 1,000 kilometers, then from 2,000 kilometers, then from 3,000 kilometers, and so on. The drop from 1,000 kilometers would result in a velocity of impact, v1. If the value of g were constant all the way up, then a drop from 2,000 kilometers would involve a gain in velocity in the first 1,000 kilometers equal to the gain in the second 1,000 kilometers. So the final velocity of impact would be v1 plus v1, or 2 times v1. However, the upper 1,000 kilometers represents a region where g is smaller than the lower 1,000 kilometers. Less velocity is added in the upper than in the lower half of the drop, and the final velocity of impact is v1 plus v2, where v2 is smaller than v1. The same argument can be repeated all the way up. So, a fall from a height of 10,000 kilometers would result in a velocity of impact of v1 plus v2 plus v3 plus v4, and so on up to v10. Here each symbol represents the portion of the final velocity contributed by a higher and higher 1,000 kilometer region of drop, and the value of each symbol is less than that of the preceding one. Whenever one is faced with a series of numbers each smaller than the one before, there is the possibility of a converging series. In such a series, the sum of the numbers never surpasses a certain fixed value. The limiting sum, no matter how many numbers are added. The best known case of such a converging series is 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, where each number is half the one before. The sum of the first 2 numbers is 1.5. The sum of the first 3 numbers is 1.75. The sum of the first 4 numbers is 1.875. The sum of the first 5 numbers is 1.9325, and so on. As more and more numbers in the series are added, the sum grows larger and larger, and approaches closer and closer to 2 without ever quite reaching it. The limiting sum of this particular series is 2. It turns out that the numbers representing increments of velocity resulting from falls from regularly increased heights do indeed form a converging series. As a body is dropped from a greater and greater height, the final velocity of impact does not increase without limit. Instead, it tends toward a limiting velocity it cannot surpass. This limiting velocity of impact, v1, depends on the value of g and on the radius, r, of the body that is the source of the gravitational field. The importance of the radius rests on the fact that the larger its value, the more slowly does the value of g fade off with distance. Suppose a body has a radius of 1,000 kilometers. At 10,000 kilometers from its center, a falling body is 10 times as far from the center as an object on the surface is, and the value of g is therefore 1/100th the value at the surface. Suppose that a body has a radius of 2,000 kilometers. However, at a distance of 10,000 kilometers from its center, a falling body is then only 5 times as far from the center as an object on the surface is, and the value of g is 1/25th the value at the surface. Through all heights, therefore, the value of g would decline more rapidly for the small body than for the large body, and the final velocity of impact would be less for the smaller body, even though its surface value of g might be the same as for the larger body. It turns out that v1 equals the square root of 2 times g times r, or v1 equals the square root of 2 times gravity times the radius. Equation 5-4. Footnote. As this is an introduction to physics, I shall not always give the derivation of the equations used, since at times these would involve concepts not yet explained or mathematical techniques I would prefer not to use. In the MKS system, the value of g is 9.8 meters per second squared, and that of r is 6,370,000 meters, so that 2 times g times r is equal to about 124,800,000 meters squared per second squared. In taking the square root of this number, we must also take the square root of the unit. Since the square root of a squared by b squared is a times b, it should be clear that the square root of meters squared by seconds squared is meters by seconds. The square root of 124,800,000 meters squared by seconds squared is about 11,200 meters per second. This limiting velocity of impact is equal to 11.2 kilometers per second, or just about 7 miles per second. No object falling to Earth from rest could ever strike with an impact of more than 11.2 kilometers per second. Of course, if an object such as a meteoroid happens to be speeding in the direction of the Earth, so that its own speed is added to the velocity produced by Earth's gravitational field, it will strike with an impact of more than 11.2 kilometers per second. For the Moon with its smaller values, for both g and r, the maximum velocity of impact is only 2.4 kilometers per second, or 1.5 miles per second. Suppose we now turn the matter around. Instead of a falling body, consider one that is propelled upward. For a body moving upward, g represents the amount by which its speed is diminished each second. See page 29. The situation is symmetrically reversed to that of a body moving downward. That is, if a body initially at rest falls from a height h and attains a velocity v at the moment of impact, then a body hurled upward with a velocity v will attain a height h before coming to rest and beginning its fall back to the Earth. But a body dropped from any height, however great, can never attain a velocity of impact greater than 11.2 kilometers per second. This means that if a body is hurled upward with a velocity of 11.2 kilometers per second or more, it will never reach a point of rest and therefore never fall back to the Earth, barring the interference of gravitational fields of other bodies. The limiting velocity of impact is consequently also the velocity at which a body hurled upward will escape from the Earth permanently. It is therefore called the escape velocity. The escape velocity at the surface of the Earth is 11.2 kilometers per second, and the escape velocity at the surface of the Moon is 2.4 kilometers per second. A body that orbits the Earth has not escaped from the Earth. It is falling toward it, and only its sideways motion prevents it from finally making impact. A smaller velocity is therefore required to place an object in orbit than to cause it to escape from the Earth altogether. For a circular orbit, the velocity must be equal to the square root of gravity times radius, where r is the distance of the orbiting body from the Earth's center, and g is the value of the gravitational acceleration at that distance. In the immediate vicinity of the Earth's surface, this comes out to 7.9 kilometers per second, or 4.9 miles per second. Orbiting satellites travel at this velocity and complete the 40,000 kilometer circumnavigation of the Earth in a minimum time of 85 minutes. As the distance from the Earth's center increases, the value of r increases, of course, while the value of g decreases, varying as 1/radius squared. The variation of the square root of g times r, which is the orbital velocity, as distance increases, is as the square root of 1/r squared times r, or the square root of 1/r. In other words, the orbital velocity of a body varies inversely as the square root of its distance from the object around which it is in orbit. Thus, the distance of the Moon from the Earth's center is 382,400 kilometers. This is 60.3 times the distance from the center of a satellite orbiting just above the atmosphere. The orbital velocity of the Moon is therefore less than that of the satellite by a factor equal to the square root of 60.3. The Moon's orbital velocity, in other words, is 7.9 / the square root of 60.3, or just about 1 kilometer per second. Consider also a satellite in orbit 42,000 kilometers from the Earth's center, about 35,600 kilometers above its surface. Its distance from the Earth's center would be 6.6 times that of an object on Earth's surface. Its orbital velocity would therefore be 7.9 by the square root of 6.6, or not quite 3.1 kilometers per second. The length of its orbit would be about 264,000 kilometers, and at its orbital velocity, it would take the satellite just 24 hours to complete one revolution. It would, therefore, just keep pace with the surface of the rotating Earth and would seem to hang motionless in the sky. Such apparently motionless satellites serve admirably as communication relays. If you enjoyed this recording, you can find more and support the production of these works at my website, JohnLothe.wordpress.com. That's www.JohnLothe.wordpress.com. Thanks for having a look and a listen. Your friend, John Lothe.